So today we're going to talk about graphing absolute value functions. This is quite a long video because there's an awful lot to talk about. We're going to try to consolidate as much as I can, but there's a lot to talk about and there's a lot to kind of cover through all of this, so hold on to your horses and here we go. So an absolute value function is a function that contains an absolute value expression. Hopefully that makes some sense. The parent function. So the parent absolute value function is f of x equals the absolute value of x. So what's a parent function? Well, a parent function is basically the most basic of the functions that are like that. So we call it a parent function. So what we find is that different things that we do to this side of it will cause different things to happen, which is what we'll talk about throughout the rest of this video. So just know that the parent function of an absolute value function is this f of x equals the absolute value of x. Okay. So next, the graph of f of x equals the absolute value of x is V-shaped. So you can see from the picture to the side, that is the graph of our parent function, f of x equals the absolute value of x. Where we have the vertex here, which our V is symmetrical around. Okay, so the vertex kind of has this thing come down to this point, then it goes back out, and notice that there's the same exact symmetrical look. Well, on the parent one, you'll also notice that that is the y-axis. So the y-axis has this kind of mirror image where it's symmetrical, exactly the same on the left side as it is on the right side. So we just talked about that point, the vertex. So this is the point where the graph is changing direction. So it's obviously coming on the left side down, it hits that point, and then it jumps back up. That is the vertex. The vertex in the parent function is 0, 0, or the point of origin. So the domain, this is a lot of things we'll be talking about quite a bit through these graphs coming up. The domain of our parent function is all real numbers. We use this symbol also to represent all real numbers. Basically what that means is I can plug in anything I want. So there's no restriction on what I can plug into the absolute value of x. I can plug in negatives, I can plug in positives. There's nothing stopping me from plugging in any number. So the domain is all real numbers. The range, though, when you look at this graph, it's not like it has arrows pointing up and down. So notice here, when we talk about our range, we're talking about the y values. So notice that I'm never going to have y values that are down here, because this v goes on forever this way, and it goes on forever this way, but the lowest y value I'm ever going to have is 0. So we represent that with this. So the domain is all real numbers, but the range from our picture is only y's are greater than or equal to 0. That's important to watch. Don't get falling into a trap of saying they're both all real numbers all the time. Well, look at your graph to determine what y's you're seeing. So the graphs of all the other absolute value functions that we're about to talk about are really transformations of the graph of the parent function. We're just going to do some different things with them. You'll remember probably doing some things called translations. That's a transformation where you would slide your graph across the paper up and down or left or right. You might talk about reflections where you fold things over and you make the mirror image. And you also will talk about moving things steeper or less steep based on certain numbers as well. But all of those come from this parent function. So let's just get into a few examples, and hopefully it will start to make a little more sense as you see them happen. So how do I go about graphing this? So we want to graph first the parent function, and then we want to graph the g of x for letter A. And then we want to talk about comparing them. We want to describe the domain and the range. So basically like what we did when we did our parent function. So let's just make a quick table. If I was to do the parent function up here. We'll just do 3 points for right now, but really you probably need to think about 4 or 5 because we're not just doing a straight line. Remember, once you see that it's an absolute value of something, there's going to be a v in there someplace. Okay, so let's just start with, if negative 1 goes in, the absolute value of negative 1 is 1. If 0 goes in, the absolute value is still 0. If 1 goes in, the absolute value is 1. So one of the things you want to be looking for is when you are making a graph of an absolute value, you are looking for the y's to start doubling up. Once I see y becoming the same number again, I've seen my vertex happen someplace in between. Okay, so what I would do is I might now say that I have enough information to draw the parent function. Well, we also know what the parent function is from the previous one, but let's just now show what that's going to look like. Okay, so if I plotted my points, I had 1 at 0, 0, 1 at negative 1, 1, 1 at 1, 1. And I'm going to draw these with a little dashed line, just to show that it's not the actual one, the g of x, that we're trying to draw. So now let's do the g of x function. So the g of x function is x, the absolute value of x plus 3. So let's start with that same set of numbers. So if negative 1 goes in, negative 1 becomes positive 1. The absolute value of negative 1 is 1. But then I add 3. So 4 comes out. So when negative 1 goes in, 4 comes out. Let's try 0. When 0 goes in, the absolute value is still 0. But then I add 3 to finish off the g function. So 0 goes in, and 3 comes out. If I plug 1 in, again, the absolute value of 1 is still 1, but plus 3 makes 4. So there's that one there. Then again, I would use my nice straight edge to draw the line. And again, this is also where our function notation comes in handy. So if I'm drawing this graph, I don't need to write out these equations if I can just label them as the f of x and the g of x. So this would be our two graphs. So they look very similar, except clearly one has been translated up. So it's important to notice this. This number sitting right out here is basically telling me to take the parent one. So notice the parent one, if I block that with my arrow, there's the parent one, g of x equals the absolute value of x. If I'm adding 3 on the outside of the absolute value function, what just happened? Well, all of these points got pushed up 3. This point got pushed up 3. This point got pushed up 3. This point gets pushed up 3. So it's basically doing a translation up 3 with that positive 3 on the outside of the absolute value of bars. So let's just kind of do it. It did mention to compare. So let's just do a few things. So let's compare. Okay, so when we asked to compare things, a couple of things we want to think about. We want to notice that these things are both opening up. So what does that mean? So basically open up means the V is going up, right? So we can see that it's opening upwards. We also want to talk about how it's the same width. Now we don't really use the word slope, but if you think about it, it's kind of the same idea. If I just focus on this side, we're going up 1 over 1, up 1 over 1, up 1 over 1. Same thing here, up 1 over 1, up 1 over 1, up 1 over 1. On the other side, up 1 over 1, up 1 over 1. Down here, up 1 over 1, up 1 over 1. So it's the same slope, rise over run, even though, like on this side, it's a negative slope, over here it's a positive slope. And it's not a slope that's consistent throughout. But it gives us the same width as far as a V goes. So we call it the same width. Then what's happening is, and this is where we saw the plus 3, we are shifting up 3 units. And again, that's because the number on the outside is making it go up. So what we call that here is we are saying the number outside is a vertical translation. It's basically telling us how far up or down you are going to be basically moving that parent function. You just basically took the entire parent function and slid it up 3 units because it was a plus 3. Okay? It also here asks for the domain and the range. So the domain, is there any restriction on what I can plug in? No. So we're going to say all real numbers. Now looking at my range, so here's a little bit of a thing we got to watch for. We're not focusing on the parent one, we're focused on this red one here. So looking at this, do I see any y values below 3? I don't see any y values down here. All the y values I see start at 3 and then go on up forever because these two arrows are going up forever. So with that in mind, the y values or my range are y's are greater than or equal to 3. Okay, let's move on to the next one. This is going to be a very long video, but we're going to get through them as quick as I can. The next one. So again, we need to make a graph. So again, if I look at my graph, my parent function, and I'm going to go a little bit quicker now because we just did out the parent function. So the parent function looks like this. And I'm just going to draw these little dashes to show that that's not really the one that we're doing. We're doing the m of x function, but there is your f of x parent function. So for the table, okay, for this table, the m of x, if I draw the x and the y. So here's where I got to be careful. So if I plugged in -1, if I plug -1 in, I do -1 minus 2 is -3, which comes out as a positive 3. Okay. So if -1 goes in, 3 comes out. If I plug in a 0, 0 minus 2 is -2. The absolute value is a positive 2. So there is 0, 2. If I plug in a 1, 1 minus 2 is -1. The absolute value is a positive 1. So 1, 1 is right there. So my question is, do I have a v? No. So I can't always assume that 3 points is going to be enough. I have to keep going until I see a v happen. So let's go to 2. If 2 goes in, 2 minus 2 is 0. The absolute value is 0. Still no v. If 3 goes in, 3 minus 2 is 1. The absolute value is 1. Well, we've already seen a y value of a 1. So that now tells me I've turned that corner and I found the vertex. So when that happens, now I can draw this line, draw that line, and I now have my graph, the m of x. So lots of times you just have to keep going, and it's going to be important to learn these rules that we're trying to help show through this video so that you can help know where your tables should be set up to help yourself go a bit quicker. So let's talk about the comparing part that we just did on the previous one. See if I can find some space in here now. So compare. So if I was to compare the m of x and the f of x. So both open up. That doesn't change. Same width. But now notice this time we are shifting to, which way are we going? Right. Okay, we shifted 2 units to the right this time. So our vertex is now not at 0, 0. The vertex is now at 2, 0. So this is an important thing to notice here. Notice how the 2 is on the inside of our absolute value expression. See, it's sitting right in here. So when that number is on the inside, it's actually going to look to do the opposite of what it looks like. So the number inside is a horizontal translation, whereas the number on the outside was the vertical translation. But I want you to notice that it's doing the opposite of what it says to do. Okay? So, for example, minus is right. Whereas the one on the outside, plus means up, which is what it should be. Minus would go down. But on the inside of the absolute value expression, a minus is to the right, a plus is to the left. Okay? Then we look at our domain and our range. Just push those way up top over here. Domain, all real numbers again. The range, what kind of numbers am I seeing? Well, I'm seeing the same as the parent function because I don't see anything in negatives or less than 0, but I don't see, just because it's been pushed horizontally, it's the same range as the parent function because I only see y's that are 0 or greater. All right, so on the next one. So here we have one where we have 2 on the outside, but it's in front of our absolute value. So this time what we're going to notice is that it is now multiplying by the absolute value or parent function. So let's just take a quick look on this one, and we'll kind of see what's happening here. So again, if I did my parent function, I'd have this, and this, and this. That's the f of x parent. When I do my q of x up top here, again, if I plug in a -1, I get -1, the absolute value is +1 times 2. Following order of operations would give me a +2. So -1 gives me a 2. If I plugged in a 0, absolute value is still 0 times 2 is still 0. We are sharing the vertex. If I plugged in a 1, the absolute value is still 1 times 2 is 2. So I've seen the y's repeat themselves, which tells me I've seen the v happen. Now notice on this one, we definitely have something steeper as far as a slope goes. So we're not going up 1 over 1, up 1 over 1. Notice how we're going up 2 over 2, up 2 over 2, up 2 over 2. And that's where this number here is coming in. This is now helping me see that it is making it steeper on both sides of the vertex. Obviously, this one is steeper as a negative slope, but it's this steeper as a positive slope over here. But a couple of things that we want to notice here when we start saying comparison. So both open up. We have the same vertex. Okay, so there is no horizontal translation and there is no vertical translation. But notice here, this one right here is definitely more narrow than this one. And basically that's because the slope is steeper, even though we don't call it slope, it's the same idea, because these lines, the rise over the run, is climbing so much faster. This space on this v is more narrow, we say. Okay, so we would say q of x more narrow. And we wouldn't say f of x is wider, because we're talking about the q of x and how it compares to the graph of f of x. So we would say it is more narrow. Okay? It's always going to be more narrow when the m is greater than 1. Okay, which kind of makes sense. That's kind of like our slope. If it's greater than 1, that's going to cause our v to close in a little bit more on itself. Okay? And then as far as our domain, again, all real numbers. Our range, this case is the exact same. Y is greater than or equal to 0. Okay? Moving on to the next one. So on this next one, the same idea. This time we're going to draw our picture with our x and y axes. I'm going to do the parent one real quick. And now let's focus over here on the p of x. So this time, because I see that 1/2, let's be smart about this, and let's put in multiples of 2's to make this a little bit easier to deal with. So let's just do the basic one. So let's do -2. If -2 goes in as the absolute value of x, that becomes +2. Times -1/2 becomes -1. So when -2 goes in, -1 comes out. When 0 goes in, the whole thing becomes 0, because I just multiply by any number, it's still going to be the same vertex. When 2 goes in, the absolute value is still 2 times -1/2. We're going to get a -1. So I think this one sometimes some people get a little bit confused on. The absolute value usually is not negative. Just remember that it's because we are multiplying by a negative out in the front of this whole thing. So the absolute value does not come out negative, but when I'm multiplying it now by a negative number, I can still have a y value that is negative. Okay? So this would be what our picture is going to look like. And again, I knew that I could have my v once I saw those two y's that come out as a -1. So comparing. So this time, we would have a couple different things. So p of x opens down. They don't both open up this time. This time our v is totally pointing downward. Now p of x, I would also say, hopefully you'll notice this, it's not by a massive difference, but it is now wider. It's opening down and it's wider. And again, that m is less than 1. So it's going to give us something that is now wider, because again, in a way, our slope, even though it's not the same slope all the way through, the slope is changing slower than the one slope of the parent function. And then with the bottom here, we talk about the vertex. Well, there isn't going to be any horizontal translation or any vertical translation. So our vertex is the same, which is at 0, 0. Okay? So then what we look at is domain and range again. Domain. Still all real numbers. I can plug anything in. But notice this time on my range, it is not y is greater than or equal to 0. This time, I'm not seeing any values above 0. So now this is actually only going to give me things that are 0 and less than 0. So this one's different, and you got to pay close attention to those. So this time we are y is less than or equal to 0. I promise I am trying to go as fast as I can, because I know there's a lot of examples here. I'm hoping in the end of it all you'll be able to look back through your notes to help yourself with this. So now we have some things, there's a lot of things happening. We want to make sure that we can follow how these things are working. So we're not going to draw the parent functions on these, because I think at this point you should have a pretty good understanding of what the parent function is going to look like. But I want to start continuing to graph. So we're going to graph this f of x, and then we'll compare it to that function graph, the parent function after that. So x is going to go in. So remember, here is our horizontal translation. Here is going to be our vertical translation. We want to keep that in mind when we start getting to the end to see how we did. Let's just make the table. Making a table is always an option. So let's just start with -1. If -1 goes in for x, the inside absolute value becomes 1. The absolute value is still 1. -3 is -2. So -1, -2 is right there. Then we'll go to 0. That means 0 plus 2 is 2. The absolute value is still 2. -3 is -1. So 0, -1. If I plug in a 1, 1 plus 2 is 3. Absolute value is still 3. -3 is 0. Don't get tricked into thinking, oh, and then it must go down next. So just keep going. So we get 2. 2 goes in. I get a 4 for the absolute value. -3 is 1. So wait a minute. What's going on here? If I do a 3, 3 plus 2 is 5. -3 is +2. What is going on here? So at some point you might want to then say, okay, what if I go backwards? What if I say, maybe I should be going back to -2? It's from we already did -1. Let's go backwards. If -2 plus 2 is 0, -3 is -3. So -2, -3. Well, we got a nice perfect straight line, but I know this can't be a straight line. So let's try -3. -3 goes in, I get a -1. The absolute value is a +1. Then when I subtract 3, I get -2. Right there, I now see that thing that I need to see. Now we've turned the corner. I can now see that this is where my v should be working, and I can now finish off my graph. And that'll be the f of x graph here. So there's going to be times where you have to really make a table and go out for quite a while. But we also want to come back to this vertical and horizontal thing, right? So we could have seen from the beginning that our vertex was going to be moving +2 inside, means that's a horizontal translation left. So the original vertex should be here, right? 0, 0. We're moving it 2 to the left. Then this thing says our vertical translation when it's on the outside of down 3. So again, we moved it to the left 2, and we went down 3, and there we are. Then notice there's a 1 in front here. So I could have done from the vertex up 1 over 1, up 1 over 1, up 1 over 1. Same thing over here. So the table helps me create it, but I could also start using these kind of shortcuts to help me really move it along a little bit quicker and get it done. Okay, so again, on my comparison, both open up. They are same width. And then we're going to say that we are shifting 2 left, 3 down. Okay? Our domain is still all real numbers. And our range, this time, our lowest y value we see is a -3. And then we see only things that are equal to or greater than -3. Okay? All right, so here we go on the next one. So this time, we're going to have that same idea here, making that table to kind of see how this is going to play out. We're looking for that y value to kind of double up for ourselves. And it looks like there's more stuff here, but just making a table always will help you get these answers. So let's just do -2. If -2 goes in, I get -4 plus 2 is -2. Absolute value is +2, -3 is -1. Then let's do negative 1. Negative 1 goes in, I get negative 2, plus 2 is 0, minus 3 is negative 3. If I plug in 0, 0 goes in, I get 2, the absolute value is 2, minus 3 is negative 1, and right away, without doing a million of them, not too bad. Okay, so all I have to do is just plot those few points. And I'm going to see my graph looking like g of x is that. Okay, so again, compared to the parent one, both open up. I know that is not neat, but that says both open up, not oven, both open up. So now we definitely have the g of x is more narrow. And the vertex, and really all the points, not just the vertex, are shifting 1 to the left and 3 down. Okay, and then looking at the graph, domain, all real numbers, range, just like the last one, we are y is greater than or equal to negative 3. And last one, I promise. So here we go. Describe the transformations from the graph of the parent function, f of x equals the absolute value of x, to this g of x function. So let's just kind of go right through these. So what do these numbers mean? So negative 2. So negative 2 is telling me two things. That it opens down. So a negative out in front of my absolute value is going to tell me that it opens down and that it is going to be more narrow. Oh, geez, spelled that wrong. Okay, so the negative tells me it's going to open down. The 2 being greater than 1, I know it's negative 2, but the 2 being greater than 1 means that it's going to open more narrow, so at a sharper slope than if it was less than 1 or if it was a 1. Then this number inside the negative 1, what does that mean? Well, negative 1 means on the inside, this is a horizontal shift to right. So remember what we said. On the inside, it's the opposite of what you think. So a minus 1 means go to the right. Positive means go to the left. If it's on the inside. And then lastly, what does this 3 mean? Well, the 3 is a vertical shift up. Okay, so the vertical shift is happening on the outside of the absolute value, and it is telling you exactly what you say. So a plus 3 means up, a minus 3 would be down. So that's what those are first talking about. So there's two methods to work on this, and we've already started to see these. So to make a table of values, you just make your table, you plot the points, and you draw the V shape. And again, notice that it's always a V shape. So let's just kind of make the table. So let's start negative 1. If negative 1 goes in, there's a lot going on here. The inside becomes negative 2. The absolute value becomes positive 2. The times negative 2 is now negative 4. The plus 3 is negative 1. And you should just run through that to make sure you can see that. 0 goes in. My inside is now -1. The absolute value makes it +1. Times -2 is -2. Plus 3 is 1. 1 goes in. I get a 0. Times the -2 is still a 0. Plus 3. I plug in a 2. If 2 goes in, I get a 1 times -2 is -2. Plus 3 is 1. So again, this right here is what I am looking for. So that then tells me I can go ahead and finish this off because I now have my V shape. So this picture is going to look like this. Okay, so that's one way to do it, is to always just think, make a table. And when you see those Y values repeat themselves, you've seen the V happen, plot your points, and draw the rest. But there's also this other way that we want to start trying to use to help ourselves kind of speed up. Here's the other method. So identify and plot the vertex. So what do we know about the vertex? So basically, from the picture we have up above, we have the g of x function equals -2 x minus 1 plus 3. So there's a lot of stuff happening, but basically the parent function is just that, right? The absolute value of x. So think about what is happening around the vertex of the parent function. So the parent function is at 0, 0. Well, from 0, 0, what is this thing telling me to do? This is telling me to move it to the right 1 unit. Okay. This out here is telling me to move it 3 units up. Okay. So remember, the inside number is telling me the opposite. Minus usually means go left, so it's telling me to go right. And this is telling me to go up. So the vertex, just the vertex, from the parent function is telling me to go right 1 and up 3 to become there. That is the vertex of this graph. Then, when I focus now on this number outside, this is telling me, number 1, it's negative, so it's opening downward. So this would be telling me that this thing is going to do that because it's negative. And the 2 means it's going to be narrow. But really what it's kind of saying is like a 2 slope. So if you think about it, if I come up here to my vertex and I was to go down 2 and forward 1, down 2 and forward 1, that would be the points that I would be plotting with a -2 slope. Now remember, the vertex causes a line of symmetry right through it. So everything is symmetrical through the vertex. So because of that, if I stop here, there's 1 away here. So I can go 1 away on this side to plot this point on the V. And then I can go and plot this point to match the other one on the other side of that. And there I have my V that we also just had from up above to kind of have the exact same picture, one with a table and one kind of understanding these transformations. I know there's a ton going on this one. I apologize that it's this long. There's an awful lot of information in here, but hopefully we can work through this and we can see how these absolute value functions work. And if you have any kind of questions, please watch the video, really try to understand the video, but ask me, and as soon as we have an opportunity to go over it, we will definitely spend more time on it.